Welcome to Lesson 8, which is all about light and polarization. So last lesson we saw how electromagnetic waves are a solution to Maxwell's laws of electromagnetism. They take the form that you can see here, with the electric field E and the magnetic field B being sine functions that are in phase and are at right angles to each other. We looked at the intensity of an electromagnetic wave, the energy density inside it, and its momentum and the pressure it exerts. From now on, we're concentrating on just one type of electromagnetic wave, which is light. We'll look at a bit of history and then start to look at the nature of light as we now know it. We will be looking at the wave model and some behavior of light, and then we'll learn about polarization. For most of history, people thought light was infinitely fast. Then, in the 1600s, Galileo recorded an attempt to measure the speed of light. He had two people about 10 kilometres apart. Both had covered lanterns. One person uncovered his lantern, and as soon as the second person saw it, he uncovered his. Galileo was trying to measure the time lag between the first lamp opening and him seeing the light from the second lamp. Because light is so fast, he failed, but he left his opinion that it must be at least 10 times as fast as sound. Then in 1676, a Danish astronomer, Romer, thought of another way to measure the speed of light. He was interested in the fact that the orbital period of Jupiter's moon Io, which was about 1.8 days, varied by about plus or minus 11 minutes throughout the year. The time between eclipses of Io became longer as Earth moved away from Jupiter, and by the time Earth was on the other side of the Sun from Jupiter, the eclipses were running 11 minutes late. Romer realized that it must be because of the finite speed of light reaching us from Io. Huygens used Romer's idea and data to estimate the speed of light. It was out by about 25%, but at least it was finally in the right ballpark. In 1849, Fizeau devised an even better method to measure the speed of light. He used a lamp, a partly reflecting mirror, and a wheel with teeth in it, and he set up another mirror about 9 kilometres away on a distant hilltop. He spun the wheel at different speeds, and he took note of the speed when the reflection from the distant mirror was blocked, and then the higher speed at which it reappeared. What was happening was this. The light only got to the distant mirror if it passed through one of the gaps between the teeth of the wheel. If the wheel was stationary or turning very slowly, the light bounced off the distant mirror and returned in time to pass through the same gap between teeth. If the wheel was turning a bit faster, the return beam would be blocked because a tooth was in its path. But if the wheel was turning a bit faster again, the return beam would pass through the next gap in the wheel. Using the different speeds when the beam was either blocked or allowed to pass through, and knowing the circumference of his wheel and the width of the teeth and the gaps, Fizeau was able to calculate the speed of light, getting a value that was only about 5% too high. This was a tremendous achievement, and this value was accepted for a long time. This was the value that Maxwell recognized when he was using calculations to try to work out the behavior of his hypothetical electromagnetic waves. Fizeau is one of the scientists who has his name inscribed at the base of the Eiffel Tower. Another difficult problem through history was the question of what light was made of. Isaac Newton was convinced that it was a stream of small particles that moved in straight lines. He used ray tracings to argue that only particles could follow such straight lines. He published many papers using this model to try to explain things like refraction and even polarization. But other scientists, such as Huygens, were coming on the scene with a radical theory that light was a wave. The wave model was much better able to explain polarization and refraction, and its biggest success came when Thomas Young demonstrated interference of light through a double slit. Then Maxwell produced his theory of electromagnetic waves, and the argument appeared to be over, until Einstein again turned physics on its head when he explained the photoelectric effect by modelling light as a particle called a photon. Our current understanding of light is as a mixture of the two, what we call wave-particle duality. What that means is that light, and all electromagnetic waves, sometimes behave as waves, with things like refraction, diffraction, and interference, but at other times it behaves as a particle, in things like the photoelectric effect and the Compton scattering. In fact, there's one theory that any experiment that shows light's wave nature can't also show its particle nature, and vice versa. In the next course on modern physics for teachers, you'll see more about photons. But in this course, we'll be concentrating on the wave nature of light.